Alright guys, so we're going to go ahead and do our last lecture of this unit, dealing with absolute age. Up to this point, we've been talking about relative age, which is to say this rock layer on the bottom is older than this one on top of it, but we haven't put actual numbers to it. An absolute age is when we put an actual age, an actual number to the rock layer. So we might say, instead of saying this one's older, we might say this one is 1.5 million years and the one on top of it is 1 million years old. So there's a few ways we do this. The first one is called rates of erosion and deposition. Or in other words, if you say you have a waterfall like this, how quickly does it erode away? And if you could figure that out, you might be able to figure out how old it is. So in a moment here, I'm going to have you guys pause and try to work this problem out, and we'll talk about it in class. But for example, here you're looking at an overhead view of Niagara Falls. Here's a little welcome center over here. And back in the year 1678, the waterfall was right here. And it's been eroding backwards. There's 1764, 1819, right to 2005 when this picture was taken. And if we know that on average that the Niagara Falls is eroding backwards 1 meter per year, and we know that since its formation, not 1678, but way before then, it's eroded back 7 miles, could we do a little math here and figure out exactly how old the rocks of Niagara Falls are? And if we can, how accurate is that measurement? Can you explain why your measurement, your estimate may be off? We'll talk about that in class, but go ahead and give it a try. Another way we can figure out an absolute age is through something called VARVs, or VARV counting. These are actual pictures of rocks found at the bottom of lakes, or in areas where maybe lakes once were. And if you are in an area where lakes are glacial lakes, have frozen over and melted in the spring, and frozen over and melted in the spring. With every melt, the little particles of dirt and dust that are trapped in the ice will sink to the bottom, and they will become layers, just like the layers on a tree in a sense. And you can actually get these rocks and count the layers, and each layer is another year. So you can get a rough estimate of the absolute age of those rocks. But of course it only works in areas that have glacial lakes. Now the most accurate way, which we're going to do a lab in class on, is called radioactive dating. With radioactive dating, you are essentially taking a rock. It has to be igneous rock in this case. You can only radioactively date an igneous rock, and that's kind of a trick that we'll talk about. But you're going to find in that igneous rock where there's some radioactive elements. And radioactive elements will decay or break down into a non-radioactive element in a very predictable manner. So for example, very top here, uranium-238, an isotope of radioactive uranium, will break down to in 4.5 billion years, so that half of that original sample will still be uranium, but the other half will have decayed into a non-radioactive element, in this case lead-206. So if you come onto a rock sample and you see that half of it is uranium-238 and half is lead-206, you know that rock sample is 4.5 billion years old. That's the half-life. Or if it's less than that, you can do a little math and figure it out. And different radioactive elements will give us different half-lives. Plutonium down here has a half-life of 2.4 million years. So again, if you find half of it is the plutonium-241, and the other half is the non-radioactive version of what it would decay to bismuth-209, you can get a half-life. Now, we're going to spend time on this in class, so if this seems a little confusing, don't panic right now. The lab is going to help clear it up, and we'll have plenty of discussions on this. Another way we can do this, and this would be useful for fossils, is through carbon dating. We won't talk too much about this because carbon dating is only useful up to a certain amount of time. Once you get over, I want to say over 20,000 years, somewhere around there, it becomes much less reliable. But going back again, here's our most reliable version. We're going to spend some time on this. We're going to talk about this. And that is the end of this unit and this lecture. We'll be doing some review in class. We'll be going over radioactive decay and some of these other pieces. We'll talk about the Niagara Falls piece and see if you got the correct answer. And I'll see you in class. Bye.